A buffer is made by adding 0.140 moles of cyanic acid and 0.11 moles of potassium cyanate to enough water to make 1 liter of solution. For each part here, we'll assume that volume changes are negligible, and we're given that the Ka for cyanic acid is 3.5 times 10 to the minus 4. So we're going to calculate the pH of the buffer. Then we're going to calculate the pH of the buffer after the addition of 0.015 moles of strong base, KOH. Then calculate the pH of the buffer after the addition of 0.018 moles of strong acid, HNO3. All right, let's walk ourselves through the solution to this sample problem. So first, in part A, just finding the pH of the buffer solution. So using the Henderson-Hasselbalch equation, the pH is the minus log of the Ka, or in other words, the pKa. So minus log of 3.5 times 10 to the minus 4, plus the log of the concentration of base over concentration of acid. So 0.110 divided by 0.140, and we get an initial pH of the buffer solution, 3.351. Part B asked us what would the new pH be after the addition of a strong base. The strong base, of course, will be neutralized by the acid in the buffer system. So before the neutralization, we have our initial amounts of our acid, our conjugate base in the buffer system, 0.140 and 0.110 moles. And how much of the strong base did we add? 0.015 moles. Remember that our biggest problem-solving tool here in this neutralization is to say that all of the strong base that is added is neutralized, so that after the neutralization we have no strong base. Well, what is it neutralized by? It's neutralized by the acid, so the amount of acid will also decrease as it neutralizes. And in that decreasing, while it neutralizes, the amount of the conjugate base will increase. So that after the neutralization, we have 0.15 moles of acid, 0 moles of strong base, and 0.125 moles of our conjugate base in the buffer system. Once we know our amounts after neutralization, we can use the Henderson-Hasselbalch equation to find the pH. Of course, this first term stays the same, just the pKa, or the negative log of the Ka value, plus the log of the concentration of base over acid. So we see here that we're using our new values for the concentration of base and acid. Now just be careful, remember that in the neutralization part here, this is moles, and here this is moles per liter. But in the sample problem, the volume of the solution was 1 liter. So anyway, we get a pH of 3.46. So look at the difference here, 3.351 and 3.46. So we have a very small increase in the pH, even though we added a strong base. So that's the point of what a buffer does, is resist those great big changes in pH when you add a strong base or a strong acid. All right, let's finish out part C of this sample problem and see what happens to the pH when a strong acid is added to the buffer solution. So remember that that strong acid in the form of H+ will be neutralized by the conjugate base in the buffer solution, or in this case, the CNO- anion. So I'm going to just, again, make some notes here. What am I starting with before? So I have my moles of CNO-, how much strong acid I added, and how much of the acid in the buffer solution was initially present. And again, the biggest thing we have to remember here is that we assume all of the strong acid is neutralized by the buffer. So we use up all of the H+ by neutralizing it with the base. So the base is going to decrease by that same amount as it is used to neutralize the acid, which means that the conjugate acid here will increase by that amount. So we have our concentrations after. Here's our base concentration, Here's our acid concentration for our buffer after the neutralization. And again, the Henderson-Hasselbalch equation helps us to find the pH. So the negative log of the Ka plus the log of the concentration of base over acid gives us a new pH of 3.22.